Okay, so chemical kinetics. What's chemical kinetics? Let's look at the objectives for this lesson. In this lesson, at the end of this lesson, you'll be expected to be able to define and calculate reaction rate and average reaction rate. You need to be able to describe typical time profiles for reactants and products. In other words, what happens to reactants and products during the course of a reaction, particularly the concentrations. How reaction rate is affected by concentration, temperature, surface area, and catalyst. So those are the four factors that affect reaction rates. Reaction rate refers to what? How fast reactions go. So that's our concern in chemical kinetics. Then you need to be able to discuss how rate laws are experimentally determined using initial rate methods, the integrated rate law method, and the method of isolation. So what are rate laws? Rate laws, you need to know what a rate law is, okay? So we'll talk about that. And then you need to be able to define what an energy of activation is and be able to calculate it from the temperature dependence of your reaction rates. So what is chemical kinetics? Like I said, it's a study of reaction rates, how fast reactions go, okay? So why are we interested in chemical kinetics? Because if you know how a reaction rate is affected by experimental factors, then that will give you information to allow you to control how fast a reaction goes, okay? Sometimes you might want a reaction to go faster, you want to slow it down. For example, you might have some undesirable reactions that you want to slow down. Those kinds of things you'll be able to control if you know how the reaction rate is affected by the different factors. It also will give you insight on the reaction mechanism. What's a reaction mechanism? It's what's going on at the atomic level, at the molecular level. Okay, so the mechanism of a reaction refers to what happened to the atoms during that particular reaction. So you'll get insights into that just by making measurements of how fast the reactions go and how it's affected by different factors. Okay, so how do you determine reaction rate? Typically, when we do these things in the lab, we run the reaction at a constant temperature, okay? To make things simple, we want to minimize the variables when we're making measurements. So when we're measuring reaction rates, we generally maintain a constant temperature. We monitor the concentration of a reactant or product versus time, okay? So we look at the concentration. If R is a reactant, then the rate of consumption of your reactant R is given by this expression right here. This is called a derivative, okay? Negative dr over dt, okay? And the average rate is negative delta R over delta T. What does delta mean? Change, right? Change in concentration divided by the amount of time that's elapsed, change in time. That's your average rate. Now you put a negative value in front here. Why? A negative sign. Because delta R, if R is a reactant, what will happen to R as the reaction progresses? It's going to be dropping, right? So delta R is going to be negative. So if we want a rate of consumption, we just want the absolute value. So the absolute value of a negative number would be, it's negative, the negative of a negative. So that's just a positive number, okay? Now, this derivative right here is just the limit of this expression right here if you're looking at a very small delta t, okay? So if you imagine a very small amount of time would elapse from a particular instant, okay? So it's like it's like in your car, your instantaneous, this would be your instantaneous rate, okay? At that particular instant, how fast is the reaction going? So it's like instantaneous speed and average speed, okay? So like if you travel, let's say 30 miles in 1 hour, you say your average speed was 30 miles per hour, right? But that doesn't mean throughout that entire trip you've been traveling at 30 miles per hour. Your actual speed during the course of your travel will depend on where you are, okay? How hard you're stepping on the gas pedal, right? So it will show up on your speedometer. Okay. Now, if P is a product, then the rate of production of P is this expression right here, dP dt, derivative of concentration of product with respect to time, that's what it's called, or And the average rate is the change in the concentration of product divided by the change in concentration of time. Okay, so like I said, an expression that's written this way, d of a variable over d of another variable, that's called a derivative. That's the limit of the change of the variable on top to the change in variable at the bottom of your expression as that delta, as that denominator becomes very small. Okay. So let's look at a simple example here. Let's say the concentration of reactant A dropped from 0.100 moles per liter to 0.05 moles per liter in 5 seconds. What's the average rate of consumption of A? So what would that be? Consumption of A would be, you can say V sub A, the speed of the reaction, the rate of the reaction. In terms of the rate of consumption of A would be negative delta A, change in concentration of A. Okay, the brackets, remember, means concentration in moles per liter, right? Divided by delta T. So what's our delta A? What's the final value for concentration of A? 0.05. 0.050 moles per liter. Minus the initial value is 0.1. So 0.100 moles per liter. Divided by the amount of time that has elapsed. How much time has elapsed? 5 seconds. Okay. So what would that be? Negative, negative, so that would be negative of 0.05 minus 0.1 is negative 0.050. Okay, sig figs there. The last sig fig is the third digit after the decimal. Moles per liter divided by 5.00 seconds. So that gives you a positive number. What is 0.05 divided by 5? 0.01. Right? 0.010 moles per liter per second. Okay? 2 sig figs here, 3 sig figs, so the answer should have 2 sig figs. And what's the unit for rate then? Concentration unit divided by a time unit. So it's moles per liter per second. So you can say, or you can say moles per liter per second. Okay? Or you can write it as moles per liter per second. That would be a unit of concentration, a unit of rate. Change in concentration divided by change in time. Okay, let's look at this graph here. At which time interval is the average rate of consumption of A larger? From 0 to 25 seconds. So this is typical of what you might observe when you carry out a reaction. You monitor concentration of, let's say, reactant R versus time. Okay. So what is the average rate from 0 to 25 seconds? Compare that from 25 to 50 seconds. For which time interval is the average rate of consumption of R larger? Is it in between 0 and 25, or is it between 25 and 50? Ready? Okay. 0 to 25. Okay. So what you notice typically is that in general, the rate of a reaction slows down as it progresses. So reaction occurs, generally it will slow down. Eventually what happens to a reaction? It stops, right? So here you'll notice you went from 0.01 to 0.05 in, so here you went from 0.01 to 0.05 in 25 seconds, but this 25-second interval you just went from 0.05 to 0.025. There's a bigger change here within the same time interval as here. So you can see the steepness of your curve gives you an indication of your rate. The steeper your curve, the faster the rate. The less steep, the slower the rate. If it's flat, what does it mean? Rate is zero, right? The change in concentration is zero. So the numerator is zero. So that's how you'd interpret a curve like this. Now, what we call dr dt, the derivative of the concentration of r with respect to time, that would be the slope of the line that's tangent to your curve at any given point. That would be your instantaneous rate. Okay? The average rate would just be the difference between 2 points, the concentration between 2 points divided by the elapsed time. But for any given instant, if you want the instantaneous rate, okay, then you have to imagine from that particular point you're interested, just imagine a small, very small advancement in time and get the rate for that small advancement in time. And that's called your derivative. Okay? Okay, so let's take a look at this. Rate is defined for a given instant, whereas average rate is defined for a given time interval. So let's estimate the initial rate for the consumption of X based on the data given in the table. What does initial rate mean? The rate at the very beginning, right? So what's the initial rate then? Which of these data are you going to use? Time 0, at 0.1 seconds, you have the concentration of X, 0.2, 0.5, 1, 5. How do you calculate the average rate? From 0 to 5 seconds. Delta X, delta T. Okay. The average rate from 0 to 5 seconds is how much? You went from 0.2 to 0.1016, so negative of 0.016 minus 0.2 moles per liter divided by 5 seconds. What would that be? Did I capture this? Yeah, I did. Okay. That would be how much? 0.016 minus 0.2. That's 0.184 divided by 5, negative, plus 0.0368. Okay, so plus 0.0368 moles per liter per second. That's the average over that 5 interval, right? So this is from 0 to 5 seconds. What's the average rate from 0 to 0.1 seconds? You think it's going to be faster? The average rate minus delta concentration of X over delta T. Okay, from 0 to 0.1 seconds, it's going to be minus 0.9 minus 0.2, right? 0.19 minus 0.2. Moles per liter. So over 0.1 seconds, 0.10 seconds. Okay, these two numbers right here. So what is 0.19 minus 0.2? 0.01 divided by 0.1, it's going to be 0.1. So positive 0.10 moles per liter per second. Compare these two numbers. Over a 5-second period, your average rate is 0.03. Over that first tenth of a second, your average rate is faster, right? Remember we said the reaction is fastest at the beginning. So if you want to know the initial rates, what would you have to do? You had to, if you only have numbers like this, you try to go with the earliest time to determine your initial rate. So your best estimate for your initial rate would be to use these two values. Okay, there are more sophisticated methods of actually getting that initial rate, because that, but if you just want to estimate what you want to do is, you know, get the change in concentration over a smaller period of time as possible. Okay? So, based on the information we've had so far, which profile here, you got the red curve, let's call that A, and the blue curve, let's call that B. Which one represents a reactant of the reaction? So you monitor concentration of A and B versus time. Which one is the reactant? Which one is the product? Ready? Reactant is A. It's dropping, right? A is your reactant. B is your, the blue curve represents your product. You start with nothing. Okay, so you're forming it, and then eventually, what happens eventually here? It gets flat. What does it mean when the curve gets flat? Your A and B, your reactants and products, are no longer changing. We say at this point right here, you've reached equilibrium, chemical equilibrium. Okay, that's when your reaction is slowest. So when is your reaction fastest? Initially, at time 0, right? Very fast here, very fast over here, at time 0. Okay. One thing you'll notice about this one is your reactant A is not used up. Okay, look at your A. It levels off at some number less than 0.1, but doesn't go to 0. Okay. How can we explain that? That means we say the reaction did not go to completion. The reason for that is all reactions are in fact reversible. Reactions happen because of collisions of atoms and molecules. There's nothing to prevent your product molecules from colliding to give you back your reactant molecules. So when you reach a point known as equilibrium, that's the condition where the rate at which the forward reaction, the conversion of what you consider as reactants into products, equals the reverse reaction, where what you would consider your product molecules reacting to give you back the original reactants. Okay, so this point right here is what we would call the point of chemical equilibrium. That's a dynamic equilibrium. Okay, so the reaction hasn't really stopped. You're not seeing changes in the concentrations of reactants and products because the rate at which the forward reaction is happening is the same as the rate at which the reverse reaction is happening. Okay. So we can define the reaction rate as follows. V, the rate of a reaction, okay, is 1 over R, where R is the coefficient of reactant R, okay, so times the rate of consumption of reactant R. So for example, let's say your reaction is 2A plus B gives you 3C. Then we say that the rate of reaction is equal to 1/2 of the rate of consumption of A. Okay? Or you can say that the rate of consumption of A is 2 times what we call the rate of the reaction. Why do we have to define the rate of reaction this way? Because let's look at this balance equation right here. Every time I lose 2 moles of A, I'm going to lose a mole of B, right? So if I'm losing 2 moles of A per liter per minute, then I'd only be losing 1 mole of B per liter per minute. So if I tell you what the rate of the reaction is, I have to tell you, am I referring to A or am I referring to B? I can't just say moles per liter per minute. So to avoid ambiguity, we define it so that if you don't specify A or B, then we assume that whatever it is you're quoting would be whatever the rate for A is or for B is, you divide it by the coefficient of A or B in the balance equation. Because 2 moles per liter per second for A, you divide that by 2, that gives you 1, right? Whereas 1 mole per liter per minute for B divided by 1, that will still give you 1. So that would correspond to the same rate of reaction. Okay, so for example, let's look at this question right here. Suppose rate is A is being consumed at a rate of 4.4 moles per liter per minute. What's the reaction rate? V would be equal to 1 over the coefficient of A is 2, right? Times the rate of consumption of A. So I'm just going to call that V sub A. Okay, so that's 1/2. And that's going to be negative delta A over delta T. Okay, the rate of consumption of A. And the 2 here is the coefficient of A in the balance equation. So that's equal to 1/2 of 0.40 moles per liter per minute. So we say the rate of the reaction is 0.20 moles per liter per minute. Okay? So to avoid ambiguity, when we simply say the rate of reaction, then you multiply that by the coefficient to get the actual rate of consumption of a reactant. Same thing with the product, rate of production of product. You divide that by the coefficient, that will give you the rate of reaction. Let's look at an example here. If the rate of reaction is V, what is the rate of production of C? Is it V, 2V, or 3V? Ready? Let's see if you got that concept. Okay. 3V. Very good. Okay. So we say that the rate of consumption of A is equal to 2V. Okay. The rate of consumption of B is what? It's just V. The rate of consumption of C is 3V. Okay. So rate of consumption of A is negative dA dt. The rate of consumption of B is negative dB dt. And the rate of production of C, that's just positive dC dt. Okay. When we're dealing with products, the rate of production would be a positive of the derivative. This would be negative for rate of consumption. Okay. Here's another clicker question. Let's say you have a reaction. 2A plus B gives you 3C. The rate of reaction is 0.3 moles per liter per minute. What's the rate of production of C? Ready? Is it 0.1 or 0.9? Okay, 0.9. Very good. Because you say rate of production of C, which is dC dt, is equal to 3 times the rate of the reaction. The coefficient of C is 3, so 3 times 0.30 moles per liter per minute, or 0.9. Okay. Okay, let's try another one. Same reaction, same rate, 0.4 moles per liter per minute. At what rate is B being consumed? What is V sub B? Rate of consumption of B. Is it 0.2 or 0.8? This is negative dB dt. That's equal to, oops, 50-50. Okay, give you a chance to fix your answer. Need to convince your neighbor your answer is correct first. Who picked A and who picked B? What was the relationship? V sub B is equal to 2 times B, right? Remember? V sub C is 3 times V. V sub A is V. Oh, it's a different one. So let's do it over. What would it be? Oh, I'm sorry. This is not the rate of reaction. I'm sorry. Sorry. This is the rate of consumption of A. My mistake. All right. You're given that V sub A is 0.4 moles per liter per minute. I'm not reading my question right. What is V sub B? Okay. Sometimes I'm not paying attention. Huh? So, made a mistake on that one. I didn't read my question right. So if the rate of consumption of A is 0.4, what's the rate of consumption of B? According to my balance equation, every time I lose 2 moles of A, I'm going to lose a mole of B, right? So which one will be going faster, A or B? Okay. So if my A is being consumed at a rate of 0.4 moles per liter per minute, how much is my B? How fast is my B being consumed? Answer is A. Very good. Okay. So V sub B would just be. So we say that V sub A is equal to 2V, right? So your rate of reaction is equal to V sub A over 2. So that's going to be 0.40 moles per liter per minute divided by 2. So your rate of reaction is 0.20 moles per liter per minute. Your rate of consumption of B would just be equal to V, which is going to be 0.20 moles per liter per minute. As expected, B is going to be lost at a slower rate than A, because every time you lose 2 moles of A, you only lose a mole of B. Okay? So the correct answer is A. Now let's take a look at factors affecting reaction rates. Reactions are due to collisions between atoms and molecules. So in general, the more frequent the collisions, you would expect a faster rate. Okay? But you have to realize that not every collision is going to lead to a reaction. Sometimes, okay, the atoms or the molecules colliding don't have enough energy for that would lead to bond breaking, okay? And so there's a minimum energy you need for the collision to lead to a reaction. That minimum energy that you need is called the energy of activation. So if you have more energetic collisions, that means in general, the higher the temperature, the faster the molecules are moving. If you have more energetic collisions, you would expect a faster rate. So in general, when the temperature increases, you would expect faster rates. You have faster movements, more frequent collisions, more energetic collisions. And like I said, and even though they might have the molecules might have enough energy to actually react. Okay, sometimes if they're not oriented the right way, okay, when they're not approaching each other in the correct positions, then the correct orientations, they may not actually react. So there's another that's another factor that needs to be considered. Okay. All right. So in general, how is rate reacted by higher temperature? Higher temperature means, in general, faster or slower? Faster. Higher concentration, would that generally cause faster or slower rates? Higher concentration. So imagine this room is more crowded. Are you more likely to bump into someone? Yeah. So more frequent collisions would cause more generally faster reaction. Okay. Now, what if you increase the concentration of one of your reactants and the reaction rate doesn't go up? Now, that gives you a clue as to what's going on at the molecular level. Maybe it doesn't matter if how much of that particular reactant you have. Maybe the mechanism of the reaction is such that there's a process there that's happening that doesn't depend on that reactant, which controls how fast the reaction goes. Okay, so that, like I said, making measurements of rates gives you clues about what's going on at the molecular level. What about surface area? If I had a block versus a powder, which one would react faster? In general, the powder would react faster because you have more frequent collisions. You get more molecules exposed, right? Whereas in a block, the molecules inside your block are not exposed to the other reactants. Now, one way you can monitor the progress of the reaction in the lab is by taking a sample of the reaction mixture. So you carry out a reaction in the lab, right? Mix them in a test tube or a beaker, and then you take a sample at different times. So let's say 1 minute later, you take a sample. Now, what you need to do at that point is to know how much of the reactants and products are in that sample, right? So it takes time to actually do that determination. So what you need to do is you need to immediately quench that reaction. What does quenching mean? You need to find a way to stop that reaction at that moment in time, okay, before you do your analysis. What does analysis mean? To analyze something means to determine how much of something is in there. So you might want to monitor how much reactant you have left. Okay, so you analyze your sample. Quenching, okay, typically you do it by dumping your sample into an ice-water mixture. Why do you think that quenches the reaction? So I have a reaction mixture, I take a little sample of it, I dump it into an ice-water mixture. Why does that work for quenching reactions? The ice water mixture is cold, right? So you have a little sample of your reaction mixture, you're cooling it down, you slow down the reaction. Not only are you slowing down the reaction, you're mixing it with a lot of ice and water. So what are you doing to the concentration? You lower the concentration, you spread out your reactant, so the rate at which they can react will slow down significantly. So that's what quenching means. And so once you've quenched your reaction at that point in time, then you can do an analysis. You can determine how much of your reactants left or how much product you've made. How do you explain why you have to put medicine in a refrigerator? What are you trying to do there then? You're trying to slow down the reaction. There's reactions going on that would lead to the expiration of your medicine. Okay? So there's a chemical reaction going on there. Why might you be asked to make sure it's properly sealed? You might be trying to prevent it from reacting with something in the air, right? Store in a cool, dry place. That means water might have an effect on it. Okay. Factors affecting reaction rates. Catalyst is something that you would add to your reaction mixture, which causes the rate to go up, speeds up a reaction. But for it to be called a catalyst, it must not be consumed. That means when you're adding a catalyst to a reaction mixture, if it speeds up, and then your catalyst must be regenerated at the end. Okay, so it's not consumed. And the way a catalyst works is it provides an alternative mechanism, which has a low energy of activation. So generally, the lower the energy of activation is, then your molecules are not going to need as much energy to for the reaction to occur. So what a catalyst does is it provides an alternative mechanism that has a low activation energy. Enzymes, you've encountered this in your biology courses, those are in fact catalysts. Those are large molecules, protein molecules, where there's a place in the molecule for substances to dock. Your reactants in these cases are known as substrates. Okay, so it's just a way to facilitate the reaction by making sure that the reactant molecules are oriented in the right way. Okay? That's what happens in enzymes. Okay, just a quick check here. 0.5 milligram of catalyst is added to a reaction mixture. How much of that catalyst would be left after the reaction? 0.5, 9, between 0 and 0.5. What did we say a catalyst does? Speeds up a reaction without being consumed. So if it's not being consumed, how much of it will be left? The whole thing, right? Okay. That's what a catalyst does. If there's none of it left, then that means it wasn't a catalyst, it was a reactant. Okay? If you have less of it after the reaction, it's a reactant. If you have more of it after the reaction, it's a product. If you have the same amount before and after, then it's not neither a reactant nor a product, but if it causes the reaction to speed up, then we call that a catalyst. Okay. If it takes 20 minutes to produce 10 grams of product X, how long will it take if the reaction is catalyzed? Less than 20 minutes, longer than 20 minutes, still 20 minutes. Okay, what does a catalyst do? Speeds up a reaction. When you speed up a reaction, what are you doing to the time? Shorter time, right? So it's going to take less than 20 minutes. Okay. So let's talk about rate laws now. A rate law is an equation that summarizes how the rate of your reaction depends on the concentration of reactants and catalyst, if catalyst is involved, at a given temperature. So you carry out a series of reactions at constant temperature, and what you do is you vary the concentrations of your reactants to see how they will affect the rate. Okay? Here's an example of a rate law. Rate law is typically expressed like this. It's equal to some constant times the concentrations. Okay, so concentration of A here is squared, and then you have concentration of B. This is an example of a rate law. They're not all like this. Okay, it depends on what your reaction is. In fact, A and B here are just fictitious symbols. Okay, the exponent that you raise the concentration of a reactant to is called the reaction order. So if your rate law is written like this, we say that the reaction is second order with respect to reactant A. Okay. So when we say the reaction is second order with respect to reactant A, that means what? It's directly proportional to the square of concentration of A. So that means if you double the concentration of A, what is 2 squared? 4, right? So your rate will be increased fourfold. If you triple the concentration of A, what is 3 squared? 9. That makes the rate 9 times faster. That's what it means, okay? So, and the exponent here for B is implied to be 1, so we say this reaction is first order with respect to B. So WRT means with respect to, okay? What's the order of this reaction with respect to C? Do you see any C there? None, right? So if C was a reactant here, then you say, okay, times concentration of C. In order for that C to disappear, I have to raise it to the power 0. C to the power 0 is 1, right? So we say it's 0 order with respect to C. Now, this K right here is the rate constant. It actually depends on temperature. That's why you have, when you're determining the rate law, you have to run all your reactions at the same temperature so that that K is in fact a constant. Okay? So, interpreting reaction order, what does it mean when the reaction is 0 order with respect to A? That means it doesn't depend on the concentration of A. The rate would say is directly proportional to the concentration of A raised to the power 0. But A raised to the power 0 is just 1. What it means is it doesn't depend on A. What does it mean if it's first order? That means the rate is directly proportional to the concentration of A. Right? That means if I double the concentration of A, what happens to my rate? It goes twice as fast. If I triple my concentration of A, what happens to the rate? 3 to the first power is 3. It gets tripled. If I make my A concentration 10 times bigger, the rate is 10 times faster. If I cut my concentration of A to half of the original value, my rate gets cut in half, slows down to half of what it was. Okay? When the rate law is second order with respect to A, then that means your rate is directly proportional to the square of A. So what happens if I double the A concentration? If I multiplied A by 2, the rate gets multiplied by 2 squared, which is 4. So rate is 4 times faster. So if I increase my A fivefold, 5 times more concentrated, what happens to my rate? Not 10 times, but it's 5 squared, 25 times faster. So that's what square directly proportional to the square means. Okay? So in general, if the reaction is nth order with respect to reactant A, then if you change A by a factor F, okay, then the rate will increase by a factor. So if your concentration of A is multiplied by F, then you have to multiply your rate by a factor of F raised to the power n. So let's look at an example here. Clicker question. Suppose rate is K times concentration of A squared times concentration of B. How is the rate affected by doubling the concentration of A? All right, let's see. It becomes 4 times faster. Very good. So if I make this times 2, my rate becomes times 2 squared. Okay, times 4. How is the rate affected by tripling A? Okay, if I triple my A, I'm multiplying this times 3, right? So this becomes multiplied by 3 squared. So it's since it's second order. What is 3 squared? 9. Okay, don't get confused. 2 cubed is 8, right? But 3 squared is 9. Next one. How is the rate affected by doubling B? I double my B. Okay, correct answer is the rate is also doubled, right? If I multiply this thing by 2, then I end up multiplying this thing by 2. Okay? So that's what first order means. The rate is first order with respect to B. Suppose a reaction involving A and B has a rate law given by rate equals K times concentration of A squared. How is the rate affected by tripling B? If I triple the concentration of B. Okay. According to this, the rate doesn't depend on B, right? Zero order with respect to B. If it doesn't depend on B, no effect. Okay. What would be the units for your rate constant? Okay, remember this K right here in the expression, let's call your rate constant. What would be the unit for that? Well, it depends on the overall order of the reaction, okay? And the overall order, n, is just the sum of the orders. So this is second order with respect to x, first order with respect to b. So the overall order is 1 plus 3, or 3, okay? So what would be the unit for k? Well, let's look at this particular example, okay? Might be better to, let me try a different approach here. So let's rearrange this equation to solve for k. What would you do to solve for k here? Let's rearrange this one. K would be equal to rate divided by 1. Concentration of x squared times concentration of y raised to the power 1, right? So what would be the unit for your numerator? Moles per liter per second, right? A concentration unit divided by a time unit. What would be the unit for your denominator? This is moles per liter squared and then that's moles per liter, right? So this is just moles raised to the power n, right? Moles cubed, moles per liter cubed. So the unit for K is moles. Okay, this one, molarity over molarity cubed, molarity raised to the power 1 minus 3 times reciprocal time. So in general, your concentration, your unit for your rate constant is a concentration unit raised to the power 1 minus n, where n is the overall order times the reciprocal of a time unit. So what happens if n is 0? If n is 0, then you say rate equals k. Okay, there's no concentration units here because it's raised to the power 0, right? So K will have the same unit as rate, so it's concentration per unit time. So moles per liter per second, for example, or moles per liter per minute. Okay, that would be the unit for your rate constant. What happens if n equals 1? Then if n is 1, concentration unit raised to the power 1 minus 1 times time to the negative 1. What is concentration? What is 1 minus 1? So concentration raised to the power 0 will just disappear. So unit for your rate constant is per unit time. In other words, if I were to give you a rate constant, by just looking at the unit, you should be able to tell me what the overall order of the reaction is. Is it 0 order, first order, or second order? If it's second order, then concentration raised to the power 1 minus 2 times time raised to the negative 1 would give me concentration to the negative 1 per unit time. So what would be an example of a second order rate constant unit? So it could be molarity, reciprocal molarity per unit time, right? So I can write it that way. Or I can say moles per liter to the negative 1 per second. Okay, so this is second order rate constant. Or I can say per mole times liter per second. Okay? So per mole times liter per second, or you can say liters per mole per second. That would be a unit for a second order rate constant. So let's look at this one. What is the overall order of reaction if the rate constant is 2.5 times 10 to the negative 3 per second? You're given the unit for the rate constant. Ready? First order. Okay. You go back and see. If it's just per unit time, it's first order. Okay. If it's concentration per unit time, it's zero order, just like rate. If it's per concentration per unit time, the overall order is second order. Okay. How about this one? What's the overall order if the rate constant is 0.25 liters per mole per minute? Okay. Second order. Very good. Okay, because liters per mole is moles per liter, right? Reciprocal of moles per liter. So this is concentration, reciprocal concentration unit times a reciprocal time unit, second order. Very good. How about this one? What's the overall order of the reaction if the rate constant is 2.0 times 10 to the negative 4 per molarity per second? second order. Okay? Per molarity means concentration unit to the -1, right? Times a reciprocal time unit. How about this one? What's the overall order if the rate constant is 2.0 times 10 to the -4 moles per liter per hour? Correct answer, zero order. Very good. Concentration unit times the reciprocal time unit. So let's talk about the initial rates method for determining the rate law. Okay, so how do we determine those reaction orders? How do we determine the rate constant? Common technique used in the lab is known as the initial rates method. So you do at least 2 runs, okay? You run the reaction at least twice. Keep all your initial concentrations the same for both runs, except for the reactant that you want to study. So, for example, here I have 2 experiments, reaction between A and B. In experiment 1, my concentration is 0.1 moles per liter of A and 0.2 moles of liter of B. In the second experiment, I changed my concentration of A to 0.2. I kept the concentration of B to 0.2. So, which reactant am I trying to study in this experiment? Is it A or B? Am I trying to study the effect of A on the reaction rate, or am I trying to study the effect of B on the reaction rate? These are the initial concentrations for the experiments. 0.1 and 0.2 for A, 0.2 and 0.2 for B in both experiments. So what am I trying to study here? I'm trying to see what the effect of A would be, right? What happens if I double my A from 0.1 to 0.2? But for me to know that, I have to make sure everything else is constant. So that means I have to run this reaction at the same temperature, and I have to maintain the initial concentration of B in both runs. So that's how you design experiments using the initial rate method. Okay? This one requires a little critical thinking. Okay? Which pair of experiments allows us to determine the order of reaction with respect to reactant A? So experiments 1, 2, and 3. Which pair? 1 and 2, 1 and 3, or 2 and 3? Will allow us to study the effect of A on the reaction. So let's look at these cases here. You have 2 males, 4 males, 4 males. So you have stock solutions of A and B. You're mixing them, okay? And then 2 males of B, 2 males of B, 2 males of B in all 3 experiments. But then you have water. This is aqueous reaction. So A and B are mixed in water, okay? And then you have 6 mL of 6 mL of water in experiment 1 and 2, and 4 mL of water in experiment 3. Okay, popular answer is 1 and 2. Why 1 and 2? What happens between 1 and 2? Use twice as much A, you maintain the same amount of B, right? So does that work? You fell for my trap. Okay, if you want to see the effect of A, you have to maintain the concentration of everything else, right? You change the concentration of A. Sure, you've changed the concentration of A by changing the volume of A. But are you maintaining the concentration of B? You're using the same amount, but is the concentration of B the same? Look at the total volume of your mixture. This is 2 plus 2 plus 6, that's 10 mils, right? And here you have 4 plus 2 plus 6, that's 12 mils. You have the same amount of B, but the total volume is not the same. The concentration of B is not the same in both experiments. So A is wrong. Okay? So it's not A, so let's do a do-over. Let's pick between choices B and C. What's the total volume in C, by the way? 4 plus 2 plus 4. Total volume is 10 mils. Okay? Now, ready? Let's see how we're doing here. Very good. Correct answer is C. I mean B. All right. Why B? If you compare experiments 1 and 3, you have the same total volume, so the concentration of B in both cases will be the same. You're still changing the concentration of A, right? You're doubling the concentration of A, but you're maintaining the concentration of B. Okay. Here's some data you might get. Okay, let's say you have a reaction between A and B carried out in the lab. Okay, what's the order of reaction with respect to B based on the data shown below? So if I want to know the order of reaction with respect to B, what two experiments would I have to do? I have to change what? Concentration of B, right? So which one should I compare? 1 and 2 or 1 and 3? Or is it 2 and 3? Obviously not 2 and 3, right? 1 and 2? Why 1 and 2? Because you want to maintain the concentration of A in both cases, right? So, can you figure out what the order is just by looking without doing any calculation? What happened to the rate when I tripled my B without changing my A? Tripling B causes what to happen as far as rate goes. Has no effect on the reaction rate. So what is the order of the reaction based on reactant B? 0 order. Okay, so we say the rate is independent of B, right? So it's 0 order with respect to B. Same data. What's the order of the reaction with respect to A now? So we've already seen that B doesn't matter what B is, right? We can ignore that. Can we just eyeball this and see what the effect of A is on the reaction? If I doubled my A, what happens to my rate? It doubles. Okay, experiment 1 and experiment 3, 0.1 to 0.2. I doubled my A, what happens to my rate? So what's the order of the reaction with respect to A? First order. First order. Okay? So I say that my rate is equal to K times concentration of A. All right? Okay. Now, let's try to do this more systematically, because a lot of times you cannot just eyeball these things and figure out what the rate law is, right? So let's do it systematically. Let's go back to this problem right here. Here's what I would do if I were to systematically solve for this problem. Okay, because you're not always going to get those really nice numbers that you can easily tell what the result is. So what if I did this? I'm going to say then rate for experiment 1 equals K times A raised to the power. I'm just going to call little a the order with respect to A and little b the order with respect to B. Okay, so rate would be equal to, I'm going to say, K times concentration of A times concentration of B raised to little b. Okay? So according to this, rate 1, 0.050 moles per liter per second. So from experiment 1, I can say my rate is 0.05 moles per liter per second equals K times concentration of A is 0.1 raised to the power A. That's concentration of A. Concentration of B is zero point 0.1. Raise that to the power B. Okay? And what two experiments I need to compare? Experiment 1 and 2, right? So experiment 2 says 0.05 moles per liter per second equals K times concentration of A, which is 0.1 raised to the power A, times concentration of B, which is 0.3 raised to the power B. Okay? I have two equations, and I can solve for B. The order with respect to B. How do I solve for the order with respect to B? Everything else here is the same except for the concentration of B, right? So what I can do is I can divide equation 1 by equation 2. So experiment 1 over experiment 2. What is 0.5 over 0.05 over 0.05? That's 1, right? What happens if I divide the right side? K over K is 1. 0.1 raised to the power A over 0.1 raised to the power A is also 1, right? And what do I have here? What is this one? That is 0.10 over 0.30 raised to the power B. Okay, so that's equal to 1. So I can say then that 1 is equal to, what's 0.1 over 0.3? That's 1/3, right? 1/3 raised to the power B. So to what power should I raise 1/3 in order to get 1? 0. Okay. Therefore, B is equal to 0. Now, how are you going to use, if this wasn't some nice number like 1, this is just obviously is equal to 1, right? But if this wasn't some nice round number, like let's say this was 0.9996, what would you have to do? You could say you can round it up to 1, but you can actually solve these things more systematically if you don't have nice round numbers. Okay, so let's do a little review of logarithms. Okay, so generally when you do these problems, you end up with an expression that might look something like this. Okay, so you might say 0.242 is equal to 0.489 raised to the x. So you're not going to get nice round numbers in a typical situation. Okay, how would I solve for x here? If you have an unknown in the exponent, how would you solve for that unknown? You do logarithms, okay? So you say 0.242 equals, what is it, 0.489 in this particular example, raised to the power x. So you take the log of both sides, so you say log of 0.242 equals the logarithm of 0.489 raised to the power x. Okay, review of logarithm. Log of a to the x is equal to what? I can move my x to the front. It's going to be equal to x times log of a. So I can say this is equal to, so log of 0.242 equals x times log of 0.489. Okay, so that's what you have right here. And now you can solve for x. You divide both sides by log of 0.489. Divide both sides by log of 0.489. And so that solves for x. And if you did this on your calculator, you might find something like 1.98. So if it's very close to a whole number, you round it up to a whole number. Okay. Typically, when you're doing these things, round up to the nearest half integer. So if you get something like 1.54, you round it to 1.5. Okay. Reaction orders are typically either whole numbers or half integers. So you can have an order like 3 halves or 1/2. okay, or 2 or 1. So I think that's a good place to stop.